Okay. Hello, hello. Hello, everyone who's made their way in. Hello. Okay. So, welcome to lecture 6, I believe. Yes. Hello, everyone. Today I'm a little sketched out. I'm sure most of us here are probably aware that last lecture things got off to a bit of a shaky end. And with the internet troubles, again, as I mentioned before, I am in the still sort of halfway through moving house. Or rather, I have moved houses, but my new house does not have an internet connection yet. And so I'm streaming from a completely separate house this time, and the internet seems very solid. It's streaming out very happy right now, but it's been occasionally known to do weird things, as we saw yesterday. So I've got my fingers crossed that doesn't happen. If it does end up happening again, then we'll have to figure something else out. But I won't put everyone through that again. If you see the lecture does start chopping up, you'll just look to the chat and you'll probably see a message from me saying we'll postpone things until we can figure out a better solution. But fingers crossed it was a sort of nasty one-off. But yeah, so with that in mind, the first thing I wanted to do today in the lecture was to do another round of feedback. However, and there is a lot of feedback. There genuinely has been a lot of feedback that's come through, and it's all been very nice. And I think I was saying last lecture, thank you to everyone who's been putting feedback in and giving constructive ideas, or even there's actually been a reasonable amount of people who just submit the feedback form to say I really liked this, or things enjoying the course, and that sort of stuff. And that's all been very nice to see as well. Thank you all very much. Now I very much would like to address that today, but last lecture we left off with a bit of content that specifically to do with slices that I'd like to try and see if we can just cover at the beginning of today's lecture. And I figured, it's probably not the end of the world if we end up addressing feedback on Mondays as a sort of regular thing, and instead of the Wednesdays, because then we can also pull in feedback from the previous week's exercises, the previous week's workshop, all that, and address sort of the previous feedback on the Mondays instead. So I think we're going to roll with that for now. So there has been a lot of feedback, and we absolutely will talk about it, but we're going to save it for Monday instead, and I think we'll try and make it a regular thing out of Mondays. What else is there to address? I think that's all we wanted to address before we get stuck into things. But yes, we'll kick off with a little bit of a quick recap of yesterday, and then also finishing off slices from yesterday. I said I was going to make a video, and then I ended up getting all my time basically stripped away from me, and I figured let's try and slot it in here. And if we end up with troubles in today's lecture, then I actually will do something to make up that content. But we'll see how we go today. And we will have time for feedback next week, because again, as a reminder, next week I am almost certain is going to be more chill. This is absolutely going to be a tough week, I think. Borrowing, lifetimes, these and sort of the whole ownership system in general is one of the biggest hurdles for every new Rust beginner. It's an idea that's at this point pretty much unique to Rust. Rust didn't invent this idea. It actually came out of a research language called Cyclone, which doesn't exist anymore. In fact, if you go to Cyclone's website, it says this has been superseded by Rust, which has carried on the torch of this idea. But for the most part, this is an idea that currently is pretty much unique to Rust, and so it's often a really big hurdle for beginners to get over. Expect this week to be difficult, but next week is all about sort of documentation and a bit of modularization and how to use those sorts of features. And I think we'll be able to sort of step off the gas pedal a little bit. We'll be able to slow down a little bit and take a breather, and then you'll have your flexibility week as well. But this is sort of this do expect this to be quite tricky content that's going to take you quite a bit of time, quite a bit of energy, quite a bit of frustration to get through and to sort of start to become accustomed with these ideas. And yes, well, yeah, hoping time-based issue. Well, the lecture was 2 hours earlier. And so if it was time-based in terms of like right at 6 o'clock, the internet goes out. We're doing well so far. So that's good news. Also the lighting is exceptional. I've got my, my lighting setup that I use here. But the rest of the lighting is a little poor today. So if the green screen starts going crazy, just let me know. And I'll see if I can try and muck with some lighting on the fly and fix it up. Okay, with that, let's, so again, lifetimes and smart pointers is what we're looking at today. It's going to mostly be lifetimes, not so much smart pointers. And we're not going to have too much like cross-language analysis for this week, just because the content this week is sort of very complex and very unique. And so we're going to spend more time doing that in the lectures as opposed to sort of cross-examining different languages. If we end up with extra time next week, maybe we can do that out of sort of like interest and maybe not quite so related to next week's content. But we'll just see how we travel with it, I think. But before we get into lifetimes and a little bit of smart pointers at the end, we will quickly recap this idea of ownership along with the borrowing concept that we were talking about last lecture. So a little table to sort of try and summarize things. We have three main sort of types that we think about in terms of the ownership and borrowing system. So for any type T, and this is assuming the T here is not a borrow itself. This might be like this might be an I32, this might be a string, this might be some struct that you've made. In fact, it's probably not best it's best not to think of this as an I32 because copy types, as we know, often skirt around the ownership system. And so it's best to think of this as some sort of owned type, let's say like a string or some struct that you made. And the requirements of this is that you have exactly one owner, right? So as we know in Rust, let x equals something, some string, whatever, let y equals x, then the ownership has been transferred from x into y because the rules state that there must be exactly one owner. If they both were that string, there would be two owners. Doesn't follow the rules. And so that is this requirement on owned types. Exactly one thing, one place can own this type T. However, you get full access to the type as well, right? So if you want to mutate it, if you want to read from it, if you want to transfer ownership of this type to someone else, all of that is well within your right to do, and it should all just work. Then we learned about borrows. So we learned about shared borrows and exclusive borrows, right? So if you have a shared borrow, the requirements is that only shared borrows can exist on that value, right? So you can't have, say, 5 shared borrows and 1 exclusive borrow. You can only have, n shared borrows. That n could be just 1 shared borrow. It could be 2 shared borrows. It could be 5 shared borrows. It could be 10,000 shared borrows. And the compiler will tracks all of this at compile time. However, your access is read only. You cannot mutate, you cannot modify anything with a shared reference. And also, you can't upgrade a shared reference. Upgrade is a bit of a weird terminology here, but you can't upgrade a shared reference or even an exclusive reference for that matter to an owned type T. So for example, I can't just say like dereference this shared borrow and give me that T. It'll go, hey, you only have shared access to this value. You're trying to get owned access out of it. That's no good. The same thing also follows for fields in a struct. So for example, and this is the example, the code we ended up with last time, which we'll come back to in a minute. So for example, if I have some struct foo, and foo has s, which is a string, which is owned inside it. Then I have let f equals some foo, right, with some fields in it, all that string there. And then I say let, I'll just call it foo borrow fb equals a shared borrow of f. I can't then say like let my s equals fb.s. right? So I've borrowed it, and I'm saying from that borrow, give me the string inside, because this S has type string, which is owned, and I'd be trying to sort of take the ownership out of the foo borrow and into my string there. And so in fact, you'll also have to throw an ampersand around the front here to say that I would like to borrow fb.s. No, you don't need these parens. I'm just sort of putting it in there to show you like the precedence here essentially. But what it's saying is, or the associativity rather, what it's saying is take foo borrow.s, right? This string here, and I will take a shared borrow of that because I only have a shared borrow of the foo value itself. So essentially, if you have a shared borrow, your only access that you have is shared. And then we also have exclusive borrows, the requirement being that only one exclusive borrow can exist at a time. So you can't have an exclusive borrow and say a shared borrow. You can't have two exclusive borrows. You can only ever have one exclusive borrow at a time. And your access is read-write. You can read the value, you can mutate the value, all of that. But which sounds the same as this T thing here, but the difference is you don't own it. Just like this shared borrow, if you have an exclusive borrow on something, it is still a borrow. You can't just magically turn that into an owned value. Miguel says, we're slightly late because I do a class to go a bit over time. Did I miss anything important? Great, and Daniel's catching you up a little bit there. Okay, and note the great news as well, in particular with a language like Rust, at least from my perspective, is that if you forget this idea here, right? If you type this code in and you forget, oh, I only have a shared borrow, and so I need to throw an ampersand in here to make it happy. The worst that it'll do to you is give you an angry compiler message, like an angry error message when you try and build your code, which probably says try including an ampersand here. It'll honestly probably just suggest you to do that, as opposed to say it building the code, you getting to run the code, and then at some point the code does something really bizarre or crashes or something like that because of the code you've written. So it will tell you up front, and it will often suggest you the right thing to do. So it's something that, again, you'll get a feel for over time, for sure. Okay, so this was this big idea of borrowing that we were talking about last lecture. I don't want to spend too much time recapping it because, we spent a lot of time talking about it last lecture. But of course, if you have any questions, then feel free to drop them in the chat or on the forum, and we'll chat all about it. Okay, now the other thing, oh yeah, I like the green screen leaking half my face through. I apologize. The other thing I wanted to do is finish off the thing we were talking about there with slices at the end of the last lecture when things sadly crashed and burned. So we were looking at this essentially. We had a variable let x is some array of 1, 2, 3, 4, 5, and that had type array of i32. In fact, I actually messed this up. This is an array of i32 with 5 elements. Is how you actually write that type correctly. Then we had let y be a vec of 1, 2, 3, 4, 5, and it has type this. And we also mentioned a string, but I think this is where things may be cut off there. And we were talking about borrowing this, right? We were talking about if we had a read-only, a shared borrow of either an array or a vec, and we were talking about how there's quite a big similarity between what these two might look like. So Daniel says, for just T, does it mean T will only one reader and writer, which is the same person? So for T, where am I? Over here. For T here, it's kind of interesting. T gives you like the most power. You can, if you use a T, man, it's hard to sort of find the exactly right words for this, but think about the ways that you could use a type, let's say. In particular, you can do things like, pull out a field. If it's, say, a struct, look at the fields in the struct. If it's an enum, you could match on it and look at the fields in that enum, perhaps. You can call functions that involve this type T. So when you're, say, pulling things out of let's say a struct T over here like this, And a similar sort of thing follows for enums as well. You really define how you're using this value by the code that you write here. So if I say fb.s, well, in fact, let's think about the t here as opposed to the borrow. If I say f.s, what I'm saying is move the s out of foo, and I'm gonna like set it over into this variable here. And now foo is actually, this f has been moved out of, it's put this value into s, and f is no longer valid because one of its fields has been moved away from. If I said ampersand before it, if I said ampersand mut before it, then I sort of define what I'm doing with the struct that way through borrowing. Now, the other thing that we often do with some type is like pass it to a function, or use functions on it. And so if I have some function foo, which takes some t, then this function is going to take ownership of some t that I pass in. Similarly, I might have a function, let's call it foo1 and foo2 because I'm terrible at naming. And this one takes in an ampersand t, and this one takes in a ampersand mute t. Right, so a shared borrow of t and an exclusive borrow of a t. And if I have, my t over here, let t equals some t, right, whatever it is, then I could pass it into a function like this. I could pass it into foo1 like this, and I could pass it into foo2 like this. Right, so this is my type that I've got. These are some functions that I could call and use with it, and this is sort of like a very core primary idea of the language. So to sort of bring this around, for just t, does it mean t will only have like one reader and writer, which is the same person? Well, so half of this is that I'm not 100% sure on the exact thing of what you're asking, but I sort of feel like I'm getting a gist of where you're coming from, which is sort of where I'm going with this. But if you're able to nail it down a little further, I might be able to answer a little more accurately. But in the case, like in terms of Rust, right? This t, Rust is going to track all like the ownership stuff to do with this t. So right now, as I've written it here, t is in just like an owned state, right? This like t, lowercase t, this little t binding here owns this t value, and that's sort of like the state of it right now. This t is owned by little t. Little t could do things like, access the fields or move out of the fields, like this one here. And, you can do whatever you want with it there. Now, there's two other states that this t could be in. Well, really this value here, this t could be in, which is it can be borrowed from. It can be borrowed from in sort of a shared sense, and it can be borrowed from exclusively. Right, so let's say I do like I call this function here, foo1 of an ampersand of t. For the duration of this function, right, just based on the way I've written it here, for the duration of this function, this t has been borrowed from in a shared sense. And so I actually can't, while it's borrowed from, this is sort of a key idea, while it's borrowed from, I can't sort of, I can't treat it like I'd be using an owned value. I can't move out of a field. I can't take an exclusive borrow. I can't pass it to this function here that takes it through ownership, right? I can't do any of that while it's borrowed from in a shared way. Then it's the other state, it could be borrowed from exclusively, right? And if it's borrowed from exclusively, same thing applies. I don't really have true ownership of it myself. I may still be the owner, but someone's exclusively borrowed it, so I can't be using it myself for other purposes. The one sort of caveat to all this is that if someone has borrowed from it in as a shared borrow, then the one thing I can still at least do is generate more shared borrows out of my owned value. And I could generate myself a shared borrow, excuse me, I could generate myself a shared borrow and then like read from that value myself. But you don't get to have all these like extra ownership privileges while someone is borrowing from your value until that borrow has expired. In the case of these functions, and basically every function we've seen so far, the borrows will expire by the time this function like concludes, right? By the end of this line here, and we move on to the next line, this borrow, whether it's shared or exclusive in these cases, will have expired, will have lapsed. And so I sort of regain my full ownership privileges on this T. However, there are some functions that we could write where the borrow does not immediately expire once the function finishes. The borrow might sort of continue into something else, and that's all about what we're going to talk. That's very relevant to all the stuff we're going to talk about today. Furthermore, if you aren't, say, using a function and you're just like passing it through like scopes and stuff, I might have like let t equals some t, right? Whatever code this is. And then in some scope here, I could say let t borrow, tb, equals a shared borrow on t. Now this borrow here exists across this scope from where it was declared until the end of this scope here. We're sort of assuming that this code exists in an even larger scope through here, for example. I might need to scroll out a little bit. There we go. So t itself exists for this period. Often in these periods that they exist for, while things are alive, their lifetime, we annotate them in Rust sort of like this. I might call this tick A, tick just being like a single quote character, and I might call this lifetime here tick B, for example. And so we say that the overall lifetime of this thing here is tick A, which will live until the end of its scope, where it was declared in. But this T has been borrowed for tick B. So this sort of space specifically here until this brace where it goes out of scope. So for example, I can't then just say like, some function foo, which takes T away right here, because it'll go, hey, there's a borrow that exists for tick B here, and you're trying to take this ownership away. This is actually a very slight lie, because Rust improved the compiler in 2018 such that it would, in this specific case, it would go, oh, I see, you've got a shared borrow of T, but notice that you don't end up using this borrow anywhere else throughout this. So I'm just going to shorten this lifetime here. Like the compiler is really smart and goes, I'm just going to shorten tick B to be this lifetime. Your code's still happy because you don't end up needing to use it past this point. So I'm going to shorten tick B to here, and then it goes, great, tick B is over. I now have my full access again, and then I can pass that ownership away. And so the lifetime of this would then only extend to here as opposed to all the way down there. Anyway, these are the exact ideas we're going to be talking about during this lecture in terms of lifetimes. I think you guys, my question also reached out and saying, awesome. What if the scope brackets didn't exist? What would be the lifetime of TB? If these, let's sort of rewind a bit here. If these brackets, these braces here didn't exist, then tick B would sort of extend all the way down here. And it would extend just before the end of tick A here, because the borrow will expire and then T will expire and get dropped and cleaned up and stuff like that. But it is, yes, it is the same scope of T. You can imagine that this sort of gap here is like infinitely small, just to sort of make almost like make the math add up in a certain sense. But so yes, everyone's correct. Wouldn't the borrow for TB expire immediately? Yes, that's also another perfectly fine way to think about it as well, just because there's no code here. If we assumed that there was, say, let's say there was a print and it printed out TB here, then you could realistically think of tick B as living for this duration here. Oops, I've learned how to fix this since. You could think of tick B as living for here, or tick B as living like this whole scope here. Both of them are perfectly fine. The compiler will basically agree with you. And yes, exactly, it's just the compiler being clever. Where you draw the line, like if you think about it this way, we have this line of code here, line of code here, line of code here. It doesn't really matter if I draw the region to here or if I draw the region to here. That ends up being the same scope, like realistically. Cool. Okay, so that's all what we're talking about today, and how the compiler tracks all these lifetimes, but sometimes you have to help it out a little bit. We're also going to be looking at that kind of thing. So slices, right, yes, over here. Where are we? My pen. Slices over here. Okay, and we'll zoom in once more. There we go. So this is what we were talking about. we're talking about the idea of borrowing, like a shared borrow from a array of i32s versus shared borrow from a vec of i32s. The big idea that I was sort of trying to get to was that if you only have read-only access to a vec or read-only access to an array, you don't really get much different, right? The whole point of a vec is that it's like an array, but it can grow or it can shrink. So it's like dynamically sized. But if you don't have permission to increase the size or decrease the size, right? These are mutations. These are rights that you wouldn't have access to through a shared borrow. Then does it really, like, it's kind of annoying. You get this, again, language biformity where which one should I use? Should I ask, like, if I'm writing a function that's, say, summing the elements up in a sequence, should I ask, I don't want to, like, take ownership because I only need to just read it and add up the values. So should I ask them for a borrow of an array, or should I ask them for a borrow of a vec? And there's really no good answer, because if I ask for a borrow of an array, then anytime someone needs a vec, right, then they can't use my like sum, my addition function, or I might have to write, say, two functions. If I choose a vec, then anyone who uses an array will need to turn that array into a vec before they use that, and there's performance penalties associated with that. Small microcontrollers, this is one of those times where I actually, one sec. Green screen moment. Here we go. Microcontrollers, like, say, this Wi-Fi card, which is making itself see-through because it has a green PCB, which is quite funny. But, you know, a little thing like this, you may not be able to allocate memory on. You may not have malloc available on something like this. And so you may not have a vec on something like this. And so now people who want to write Rust code for one of these things can't use your summation function. So what's the solution here? The answer is slices. So slices unify this idea. They unify, like, ideas of arrays, vecs, and all other kinds of sort of contiguous containers, essentially. The syntax for a slice looks a little bit like this. So the syntax for an array looks like this. The syntax for a vec looks like that. The syntax for a slice is just like this. Or in sort of general, just any t can be substituted in there. So notice you don't have this semicolon 5, you don't have this semicolon 5, and you don't have, like, vec or anything like that. It's just square brackets with the type inside. This is a slice. Now, problem arises immediately with a slice, which is how many elements are in it. How many elements are in it? If I have, like, a function, fn takes a slice, and let's say S here is a slice of i32s, then the compiler is not particularly going to like this, because how many bytes should it allocate for S here in this function argument, right? How many bytes is S? And the answer is, who knows? Like, this could be, someone could realistically pass in an array of, like, 1, 2, 3 here. And again, this is meant to work for just any arrays or vecs or anything like that. They could pass in a vec that's, say, empty, right? It could be 0 bytes. It could be, 12 bytes here. It could be 1,000 bytes. So the compiler doesn't know how much space to allocate for S. So slices are basically generally pretty unusable on their own, because they are, the correct Rust terminology for this is that a slice of t, right? Slice of t in this case, is not sized. Slice of t is not sized. Since it's not sized, you can't just put a slice of t in a variable like this. If I said let s equals, you can't have t straight in an s. If you have a function argument, you can't have a slice of t. If you put it in a struct, then your struct becomes not sized, and then you can't use your struct anywhere. It's all a big nightmare. So this sounds horrible. Like, if, how the heck am I meant to use this at all? And the answer is, oh no. Oh, it seems happy here. Oh, stream health. Stream is healthy. Okay. Yes, it says 10,000 bit rate on my end. So I think it's okay. How much did we lose? What was, like, What was the last bit that we heard about? Like 10 seconds. YouTube is not... okay, I think YouTube's just running behind. As such, viewers will experience buffering. Yes. Thank you for that, YouTube. Okay, so I said it wasn't sized. Cool. So, it's not sized, which means you can't use it in a variable, like let s. If s is a slice of t, you can't just say, let this variable here. You can't use it in a function parameter, which is effectively like a variable. You can't, if you throw one of these straight in your struct, then your struct becomes not sized and you can't use your struct anywhere either. It all becomes a massive headache. So the question is, this sounds horrible. How the heck are we meant to use these slices then? And surprisingly, is a very simple answer. You just need a layer of indirection. You need a layer of indirection, which for most languages, that's achieved through a pointer. And as we know in Rust, we have references, which are basically like pointers, right? Pointers, i.e. like stars in C, but with like extra rules attached to them, extra sort of semantics. So ampersand and ampersand mute, and we'll also learn about some smart pointers later on, which can also offer this kind of indirection. Okay, cool. I think stream seems happy for now. Okay, so if we add a level of indirection, how does that help us? So let's say we have a shared borrow of this, I32 slice here, or a shared borrow of these t's. Well, now suddenly it is sized. The type is sized. How big's the type? It's the size of, well, it's not quite. Let's just say for now, it's the size of a pointer. And then you simply follow the pointer, right? You follow that pointer to get to the data, right? In this case, the pointer might point to this data here, or in the cases above, the pointer might point you up here, or the pointer might point you all the way up here, for example. But then you follow the pointer. How do you know how many elements there are? This is like how many elements are there? C does stuff like throw a null terminator on the end. So you just read until you run into a null terminator, and then it's like, oh, okay, that must be the end there, which has all kinds of horrible implications that we might find some time to talk about during the course. So how does Rust do it? The answer is that I lied. This type here is a little special. An ampersand almost always just means a pointer, right? It's the size of just one pointer on your system. But there's a few types where an ampersand of that type T, in this case, let's say an ampersand of this like slice I32, is not in fact the size of one pointer. It's actually the size of two. So this gets encoded as an actual pointer itself, which might point to, say, some data here, 1, 2, 3. And along with that, it also carries a size. So in this case, the size would just be the number 3. And so you look at this type, you can imagine it literally is just like a tuple of pointer and size. And then you go, okay, the size is 3, and the pointer will take me to this data, and I get 1, 2, 3 elements, and don't read any further than that. So that's what a slice gives us. And the great news is you can very, very simply, very trivially turn an array or say a vec or anything like that into a slice. But you need to borrow from them, right, in order to create that like borrowed slice that we named out here, right? Our borrow over here. Okay, so the other interesting thing about a slice is since it carries its size along with it, we can actually use slices to obtain sort of like a subsequence of whatever list we have. So let's say we had let A equals an array of 1, 2, 3, 4, and 5. And then we wanted to hand out like a slice to a function or something like that that just contained these bits here, 2, 3, and 4. And it sort of skipped off the 1 and skipped off the 5. Now that is possible with a slice. And the way how is that, well, a slice of, in this case, let's say I32s, is just going to contain a pointer and a size, or a pointer and a len, whatever you want to call it. And the trick is we make the pointer point right here, and we make the size 3. And so then you just get this sequence here, 2, 3, and 4. And so the syntax, let's say I actually had this A here and I wanted to generate this, slice right there. I could write something like let slice equal ampersand A of index 1 up until index 4. So index 1 here, this is index 0, 1, 2, 3, 4. And this is sort of like inclusive, exclusive syntax right here. I believe you could also write .. =3 if you wanted to write it that way. But this is very common to have inclusive, exclusive syntax like this. And so it says from element 1 up until just before element 4. And you would get this slice as a result. And you could pass that off to a function and it would just see these 3 elements. So, and keep in mind, you can also have different forms of slices. You can have things, you can have like an exclusive borrow on a slice, ampersand mute slice of i32s. And this would be, in our case here, let's say it was the same values, it would be a slice of 2, 3, 4 where you can modify those individual elements. So you could say change this 3 to a 7, or you could, change all the values here to like 0, 0, 0. Something like that. But notably, you can't like expand or shrink or anything like that. All you see is these 3 elements with no additional context, and either you have an exclusive borrow in them such that you can mutate them, modify the values, or you have a shared borrow in them where you can just read those values off. Okay. I might have done last week's lab without knowing anything about borrowing. The folders library uses this. I was confused what they were talking about in the docs. Cool. So, let's do a quick example then. First word of some string. Right. Yes, very good. So, if we wanted to write a function like this, we probably could. You could do this imperatively by looking through the bytes and trying to find like a space character or something like that. We could also, let me uncomment it so we get Rust Analyzer. In fact, it's even, I love how as bytes is at the very top here. I mean, we could do that. We could say for, let the bytes of the string be this string is bytes. And then for index an item in those bytes dot enumerate. In fact, we can have this be into iter, that. And so this will give us just sort of like together the indexes and the bytes of the string as a piece. If the item is a space character, then we've found the end of the string. Otherwise, if we never find a space character, we'll end up down the bottom here. So what should we return back here if we have like a first word? If we have some string and we want to give back just like the string that is the first word, we could give back a new string, right? And this new string will just contain that text and then that'll be the end of it. But with our newfound knowledge, oh shit, we haven't talked about string slices yet. So bear with me in a second. Strings also have this same parallel. Sorry, I really should have mentioned this before jumping to that example. The parallel that we've just observed of, let's say, between vec of i32 and a slice of i32, this parallel here is also mirrored as capital S string and lowercase str. These are exactly the same sort of relationships. So a string is a sequence of text that can be grown, it can be shrunk, and it's allocated on the heap with malloc, whereas a ampersand str, ampersand stir, ref stir, whatever you want to call it, is a slice of characters that may point within a string, it may point to like a text literal that's been typed into the code, but it's the same sort of idea. It's just a pointer and a length, and the pointer points to an actual string, and the length is the amount of bytes of that string. Same sort of parallel here. So if you've seen big string and ampersand stir, that's what you're looking at there as well. And notice again, same deal. This always needs to be borrowed in some sort of borrowed form, or at least have a indirection, like behind a pointer. So with that in mind, we could give back this whole string, but realistically, we don't need to make a whole new string. We can just give them a pointer that points to like a borrow, a slice that starts at the very beginning of this string and only goes so many bytes. So let's say we were doing this, we can mix a little bit of functional and imperative here. We could say let some index start at like an end index start at 0. For each item here, we'll say end index plus equals 1. And if the item is a space, then break. Now at the very end here, we should hopefully have the our end index be whatever the index should be once we hit a space character, essentially. Is that gonna, the way I've written it here, is that going to include the string? Does this need to go above or below? Well, if we have a space right at the beginning, the end index would be 1, which would be exclusive. So actually this probably needs to go over here. I believe otherwise we'll include the space itself, but you can feel free to correct me if you think I've got it backwards potentially. And then finally at the end here, we have our ending index. Simply we'll say, give me the string from 0 up until that ending index, like that. But of course I need to borrow this with an ampersand. Can we just have an early return where we find the space and return the entire string again in the end? Yeah, we absolutely could, for sure. Oops, let's change this to an ampersand stir. And we get this thing. Let's see, item here is a ampersand U8. Fortunately, I could say like borrow this string, the space character on the side here, and that would be happy, but that seems a little silly. Because a U8 is just, again, a copy type, it's a very trivial type, then Rust is fine to let us just dereference this item. And I'm saying this is a space byte as opposed to a space character, which is, there's two different types here, char and U8. But anyways, this is the big idea at the bottom here, that we can do this. And if we wanted to write it as Daniel says there, we could just say give the whole string back like this. And instead of breaking up here, just say give them the string from 0 up until the ending index, like that, potentially. Return it rather as a early return, like this. This is also a potential option here. If you try ampersand string of 0 to 0, will it just be the first character or an empty string? Well, if we go back to this again, the ending index, so the starting index is inclusive, the ending index is exclusive. So like which one takes precedence in a certain sense, you might be asking if I have 0, 0. And the answer is this will be an empty slice in our case. The green screen's starting to get fizzy. I will brighten myself up a whole bunch. Yeah, it's a little less fizzy. So this will end up being an empty slice essentially. So your end index in a certain sense kind of takes like priority there in a certain sense, really. Now there's another thing that can be improved in this. We'll go back to the other option here, but both of these are perfectly fine. You also don't, if you're starting at the beginning or if you're finishing at the end, you also can just leave them like elide them, and the compiler will know this just basically means a 0. If I don't put it here, it just basically means like the length. So this all seems happy. But up here, notice that I've said this function can only be called for people who have capital S strings. They own the string, well, or they have a borrow on an owned string, as opposed to just like any slice of any string, which is more flexible, right? So if I say just give me any like string slice, that could be something within a larger string like this, or it could be like something out of like a string literal that someone's typed in, or all kinds of other options as well. So this is a more flexible interface because all it's saying is I need a pointer that looks at some text and how long, like how many bytes of text there is, which is just far more flexible than like I need something allocated with malloc and all that sort of stuff. So this is sort of like the ultimate final form of this function, in my opinion. We've got some test cases down the bottom here, I believe. And notice, it's funny. I'm using a string here, a capital S string, but it still seems to compile. If we run the tests here, the tests are all okay. But I said it takes an ampersand stir, but I'm passing an ampersand string. And this is, again, part of that flexibility. Rust is very smart here in seeing that you have an ampersand string, but what the function wants is an ampersand stir. And it actually knows that it can get that simply by doing like a dereference on this type here to trivially get this. And so it ends up applying that automatically for you, which is actually rather nice. But since we've made it more flexible, I don't even need to do this whole string from over here. I can just pass these string literals directly in, because string literals have the type ampersand stir, ref stir. And so this will also pass all these tests and just give us back string slices of just the first word in anything here. Okay, so that was an example with a string slice. So these are the main, like, the slices that we end up looking at in this course are slices of some type T like this, which again, the closest parallel to sort of tie them with is something like a vec of some type T. And the other one that we think a lot about is strings, like capital S string with a stir slice being its parallel. And these are all you need to know for slices. Does that also work for vec? Yes, where we can pass an ampersand vec where the signature is slice of i32. That's an awesome question. That's an excellent question. Let's find out. Function foo takes a slice of i32 and let's say x's, and let's say it returns their sum, x's.iter.sum, like that. And then I have another function that says let x's is a vec of 1, 2, and 3. And I say call foo with an ampersand x's. So ampersand x's has type reference of vec here. x's has vec of i32. So ampersand x's will be ampersand vec of i32, a shared borrow of an i32. And it does compile, it's all happy because it sees that it can convert that with a dereference. So very nice. And the difference between iter and into iter, that is something that we definitely would like to talk about. Yeah, let's quickly try and slot that in as well, since now that we've got this idea of borrowing down as well. We've sort of hand-waved a bit before in that there's three main methods that Rust conventionally uses for turning sequences into like iterators. And those were into iter. There was also iter, and there was iter mute. And these are all very common, like commonly exist on things like arrays. They exist, so like the arrays of some n. They exist on slices. They exist on vecs. They exist on, you know, all kinds of types like this where you could iterate over. They very often produce these three functions available for you to use. And the trick is how they sort of correspond to ownership wise. So let's say we have some sequence, a sequence of t's, right? Into iter will consume the sequence, right? If I have, let's say in the case that it's like a vec, let's say a vec of t, into iter will move out of that vec of t. So you will no longer own it. It gets literally converted into an iterator and you lose ownership of it. But the iterator will then spit out, like the item that the iterator spits out will be individual t's that are owned. So as you sort of iterate over them, you get given ownership of those t's, of the actual items that the iterator is producing. Iter will give you each item is going to be a shared borrow of a t, and it only takes a shared borrow of the vec. Right, so you'll still get your vec to be used after the iterator is all finished and everything like that, but you'll only get shared borrows on the items inside, and you may be able to predict a similar thing happens for iter mute here, where you have an exclusive borrow on the items inside, and it requires an exclusive borrow of your container, of your, like, say, vec of t's. And the way these end up looking in the signatures is that into iter takes self, self-referring to the container it's being called on. So let's say like a vec of t in that case. Iter takes a shared borrow of a self, right? A shared borrow of the container like a vec, and iter mute takes an exclusive borrow of the container self in this case. And so these here each correspond to the different items that it will spit out. It's to sort of like, again, there's going to be things where you like look at this and you go, okay, I get like 20% of that and I'm losing a lot of it. And this is where it comes down to sort of your practice and just playing around with the language and seeing what the compiler likes and doesn't, and asking questions on the course forum and all that. And over time, you'll sort of eventually, you may have it now, it may take you another 5 weeks, and but at some point you'll go, oh my God, I see how all this is sort of coming together and like lining up now. Cool. All right, so those are our iterators as well. It's probably a decent time for a quick break. And then when we come back, we'll be talking about lifetimes probably for about 45 minutes, and then talking about smart pointers probably for about 15 is what I'm hoping for. Yeah, so do we have any questions? Let's say break starts now. If you want to go take a break, then go for it. We'll come back at 7 o'clock, right, in 3 minutes time. If you have any questions, then I'll field them during this break time. Otherwise, we'll kick off again with more content at our 7 o'clock. So any questions? I might also mess around with the lighting a little bit while we're waiting. Focus. Yeah. That's potentially a little better. That's potentially a little worse. That's why when I do iter, I have to dereference into a lambda function. Yes. And the star used by the iter. Yes, yes. So that's this one here. Well, this we did use into iter, but we're calling into iter on something that's already borrowed. So again, we can't upgrade a shared borrow into an exclusive borrow, sadly. But potentially, if we did, we could also just write iter here and we get the same result in this case, just because this is already a shared borrow. But if we had, for example, x's is an array, 1, 2, 3, 4, 5. And we say for item in x's.iter, or let's say x's.into iter rather. Then item here has type i32. If I change to iter, item is a shared borrow of i32. And if I change to iter mut, then item is an exclusive borrow of each individual i32. And the one other thing that's worth noting is that if we use into iter, and then I try and use x's again after, then we've got a compiler error because it doesn't implement display. If I debug print it, it's happy. Huh? Why am I doing this? Slice. Huh? Oh, you know what? Oh, this is so nasty. Why would you do this to me? Hang on. Ah, okay. Oh, 158. What? Oh, that's quite interesting. Okay, so this is a particularly weird one. Oh, we're back from the break technically. That's rather interesting. This was not my understanding, but what's actually happening here is the type array. Arrays of any size implement the following traits if the element type allows it. Copy is one of those. I'm not sure if this was, I may have just always had this misunderstanding. So notice that the implementation of copy, so first of all, the things inside the array must be copy. And it says, I'll implement copy for any size array. I'm guessing that prior to 158, which is relatively recent, I think we're on like 162 or something now. It was probably only for arrays up to size 32 in particular that would be copy where the individual elements are copy. But now it seems like all arrays are copy if the T itself is copy, which is actually quite interesting and honestly news to me. I think I might have even just given faulty information in a previous lecture. So there's a quick addendum there. I wonder if I can look at like a Rust 157 std docs. Actually, wait, maybe no, because it's not docs.rs. It's going to be a little tricky for me to get the old documentation up, but that's something that I'd be very interested in looking at. I bet it would only be up to size. Yeah, arrays of size implementations are generally implemented up to size 32 for arrays until recently, when we got something kind of cool called const generics. Anyway, if this was something else, let's say vec. There you go. That's what I was hoping for. The into iter moves out of it, but if I did say iter, iter, it's happy. If I do say iter mut, it's not happy because this is not mutable. But if I make it mutable, then it's also happy. But if I say into iter, then it is no longer happy because we moved out of it by taking ownership of these individual items here. That's what's happened there, basically. That was fun. All right, so end of break. Let's get back to the fun stuff. So array iter does a copy. It's more like when we had it as an array here, into iter takes self, so takes x's here, but x's is a copy type, so it just gets copied into the function into iter, and so it leaves our original one intact. So that's why this was working in particular. But as soon as it's not a copy type, it doesn't get copied in, and it shows us the breakage that I was hoping for. Okay. So back to our usual content, lifetimes. Great. So we've already sort of jumped ahead on this a little bit when we were sort of asking at the beginning, but this is the idea that I was talking about before, where let's say we have some value, some reference R, some binding that is yet to be set called R. R sort of is granted this implicit lifetime tick A. That's just, and again, the tick syntax is just what how we usually talk about this idea of lifetimes in Rust, and we just give it some arbitrary name. Often it might be better to give it a better name for yourself, like lifetime R. It's essentially like a variable name, but since we're not talking about anything in particular, sort of like how we often use like X, Y, Z for variables that mean nothing. We often use T to indicate a type that doesn't really mean anything. Lifetimes we generally start with tick A, tick B, and tick C, which is what's happening here. And what's going on is R is implicitly granted this lifetime of tick A, which basically extends from where it's declared here until the end of scope, where it goes out of scope. And then we have this inner scope here where I say let x equals 5. So now this value 5 here, which x is referring to, which x kind of owns in a sense, is granted this lifetime tick B. And that lifetime expires at the end of this scope here. So tick B lives from where x is declared, where this is given a value, right up until the end of that scope there. That's tick B. And then this very cheeky line of code here, let R be a shared borrow of X. Right? And this is where we finally meet our nemesis, the borrow checker. So notice that there's an error on this line that says X does not live long enough. So let's actually get the error message out here. X does not live long enough. I'll zoom out a little bit actually. So when we say R equals ampersand X here, this borrowed value of the shared borrow of X does not live long enough. X is dropped here, right? That's the end of tick B here that we've seen there, while it's still being borrowed by this R here, and R is later used down here, right? So you could also, it's also pretty reasonable to think of this borrow as living like, of tick A sort of living like this, potentially. But the borrow checker has come in here and gone, well, what have you tried to do? You've tried to almost extend tick B, right? This R is borrowing from X. So it's borrowing from this lifetime here, tick B. You've almost tried to extend this all the way down to here, but it actually ends too soon. It ends too soon, which it spits out as does not live long enough. This is Rust's sort of famous borrow checker that's able to stop all these memory safety issues at compile time. It's able to check the lifetimes of all these different pointers and references and all that sort of stuff, right? This is our first encounter with the borrow checker. Okay, now what if we rewrote this function a little bit into something like this? So let X be equal to 5. R is then a borrow of X. We print R out and the function ends. So the lifetimes here look like this. We have this value here that's living in X, has this lifetime tick B, which is going to live until it goes out of scope down here. And then we borrow X from this R. This borrow, right? The borrow in X lives for tick A. So you might like to think that this ampersand here almost has this lifetime associated with it called tick A. Excuse me. And it's borrowing from X. We use R here in the print, and then finally the borrow here with lifetime tick A goes out of scope, and then X goes out of scope. And the borrow checker is perfectly happy with this because this X here that tick A borrows from is lives at least as long as we want it in this tick A lifetime here. Right, so the thing that the borrow checker is checking for here is X here, this lifetime tick A is borrowed in this segment here, and it needs to be borrowed for at least as long as X is valid, which is this lifetime tick B. The way we'd also write this in Rust is tick B outlives tick A, right? This colon here is, again, tick B outlives tick A. That's what this sort of colon here means. And as long as that's the case, as long as that's true, then the borrow checker is usually going to be happy. It's got to check for things like, have you got an exclusive reference already? You know, do you, like, it's still got to check the usual ownership rules and all that. But as far as lifetime concerns, it's basically checking these sorts of outlives ideas. And this one failed here because R borrows from X here. And let's say this reference we're sort of thinking has lifetime tick B. Oh, sorry. Sure, yeah. This reference has lifetime tick B. But then we use it over here. We use it like down below in this larger lifetime. I need to get these slashes right. We use it in this larger lifetime. Does tick B outlive tick A? Sadly, it does not in this anymore. Because we have this sort of shorter lifetime of tick B here. So this, we're trying to sort of extend the lifetime of tick B past where it actually lives. And the borrow checker will stop us from doing stuff like that. Okay, let's, so this is just a very quick introduction to this idea of lifetimes. Very, very quick introduction, and I'm gonna like immediately comment it back out again. And jump into sort of how lifetimes can potentially like, when we run into this sort of idea. So consider this function here, longest. So longest takes in two string slices, two borrows of strings, x and y, and then it spits out one string slice here, a new borrow at the end of it. And it says if x is longer than y, then spit out x, otherwise spit out y. But the Rust compiler does not like this program for some reason. Let's see what it has to say. It gives us the exact solution, which is quite funny. But I'm just going to leave us right there and shorten this down. So here's our error message. Missing lifetime specifier. This function's return type contains a borrowed value, right? So the return type here is has a borrow in it, which is this ampersand here, but the signature does not say whether it's borrowed from x or y. Oh, interesting. So let's say we had a function foo that we were using, and we wanted to call longest with some strings. Now you might imagine, okay, they're going to call it like foo or foo1, something like that, and we'll give this string slice back and everything's happy. But imagine we had two string slices with different lifetimes. So let's say we had let like long lifetime string be a string from hello, and then let's say like a few scopes deeper we have let very short lifetime string is string from foo_barbaz. And then right here I said call longest with the long lifetime string and with the very short lifetime string over here. Let longer equals that one, right? Oops, what have I done? Here we are. So the question is, what is the lifetime of longer? How long does longer live for? Right? This long lifetime string exists all the way from where it was declared here until the very end of this foo function here. And imagine, let's say we have, you know, more code here, and more code here. Like there's a lot going on with this code compared to how I've written it. But this very short lifetime string is only going to live just until here. And this longer really could be either of these. It really could be either. So the question is, and this is also paired with the consideration that the compiler needs to know all this information, needs to know all these lifetimes at compile time, right? This is not some extra code that checks things as the program's running. It needs to be statically determined at compile time when you're building the code. So it's not going to, like, these strings could be completely dynamic. This could be like get input from user, right? This could be getting some input from the user and you don't know whether it's going to be shorter or longer. The compiler can't just go, let me just guess, or let me just like check the lengths of the strings. You might not know how long they are when you're building the code. So what does it do? Well, the answer is it gives us a compiler error in this sense. And the trick here is that we need to help the compiler along with the lifetime of this string output here. Now, there's a couple things we could write. We could write, so I'm going to introduce a named lifetime, just like this. So the trick here is that we throw in some angle brackets just between the function's name and the parameters, and I can name a lifetime by saying tick and then a name. So I could say tick foo if I wanted. I'll call it tick A. And let's say I said x is a borrow with lifetime tick A, and it's a borrow of a stir. And the output is going to be a borrow tick A stir. So what we're telling Rust is the lifetime of the borrow that we spit out is going to be the same as the lifetime as the borrow of x's borrow that was spat in. And this makes the function signature happy, but then we get a problem. What's this problem? It says that like y here could have any lifetime, right? It could be longer than tick A, it could be the same as tick A, or it could be a lifetime that's shorter than tick A. And right here, you're trying to return y. Y has some unknown lifetime, and I need to say that this has this lifetime tick A. That will be okay if y does have the lifetime tick A, or if y has a lifetime longer than tick A. But if y has a lifetime shorter than tick A, then that's a real problem. And it really could do that, as we've done it right here. This is a really long lifetime, that's a very short lifetime. Really long lifetime, really short lifetime, and it's expecting the really long lifetime out, right? So as Alex has said here, maybe it should live as long as the shortest. Daniel says, I also think it should be shortest, but I think it's because it goes out of scope at the same time as shortest. So, right, we actually, like, the only way that this code could be sound, right, this code could, do the right thing, is if this outputted one is the lifetime of whichever one here has the shortest lifetime. So let's say we had two no, we won't jump straight into that. So what happens if I annotate y with tick a here? It seems to be happy. Let's build it, and it builds. So why is it happy now? Well, we say x has some lifetime tick a, and y has some lifetime tick a, and the lifetime we're spitting out is tick a. But we know that these don't have the same lifetime. Let's say this has lifetime tick x, and this one here has some lifetime tick y. These are not the same lifetimes, but they're sort of being implied to be if you look at the types here. This is, some like string over here with whatever lifetime. This is a string over here with whatever lifetime. These tick a's are the same here, but tick x and tick y really don't seem to be the same. And the trick is, Rust is happy in these cases here to just shorten lifetimes where necessary. So tick a will be chosen to be, one of the lifetimes, and it's happy to say, well, in our case, x has a longer lifetime, so we'll make tick a be this lifetime here. We'll make tick a be equal to tick y, and then we're fine to use tick x in place of that tick y, or the tick a up here, because it's at least as long as it, right? Tick x it lives for the whole period of tick y, so it's perfectly happy. Since it lives across that whole period, it's at least as useful as tick y, is another way to think of it. It's at least as useful. And again, the syntax here would be, I guess up here, would be that tick x outlives tick y. And so since it outlives tick y, this is all okay. We could also name them individually, like as tick x and tick y, and gave this one tick x and this one tick y. And the question is, what does this one spit out here? And it's, well, we could do like, let's say a tick z that this one here spits out. And I could sort of work all these lifetimes manually here. So I could say that tick x needs to outlive tick z, and tick y needs to outlive tick z. And it should also be happy with this, because essentially we're saying this has some lifetime x, this has some lifetime tick y, and the output here has some completely unknown lifetime tick z, but we know that tick z, like tick x must be bigger, it must be like the same or a longer lifetime than tick z, and tick y must be the same or a longer lifetime than tick z. And it does all its analysis. It goes, okay, can we return x here? X has lifetime tick x outlives tick z, so it's happy. What about y? Well, y has lifetime tick y outlives tick z, so it's also happy. And then down here, it just instantiates those lifetimes, and this lifetime that it spits out will end up being inferred to be, it has sort of these constraints that it gets, where it knows that it's the longest lifetime it can be such that tick x outlives it and tick y outlives it. And with those constraints, you get that it will be this whatever the shorter lifetime of the two are, essentially. So it casts the longer lifetimes to the shortest among all. Yes, that's absolutely correct. So if we go back to the simpler example back here, if we go back to what was simpler with just tick a, then it will just end up giving you whatever is like, one will be instantiated as the shorter lifetime will be tick a, the other lifetime will just like automatically shorten itself, so it's happy. And yes, lifetimes is almost certainly one of the hardest things, especially when you're getting started with the language. Which lifetime notation is more idiomatic, the simple version or the version with where? The simple version is almost certainly more preferred. And a lot of the time, the compiler will be able to do the lifetimes automatically for you, which we'll talk about when we get to Elision. This is the simplest format of this function here, and that's generally what's preferred. I'm not understanding what extra information the compiler is getting here. Can't it just infer the shortest? Right. So that's a very reasonable question. So I'm assuming if you're saying we had over here, this was the code here, why doesn't it just infer that it is the shortest of the two here? Like it should be able to just guess this. And the answer is, you're right in a lot of situations, but not in this specific case. And I think there's a pretty reasonable reason why. So let's pop quickly back to this slice one that we were looking at earlier and pay close attention to the signature. String here is a borrow of a stir, and it spits out a borrow of a stir. Notice that we didn't have to write all this. We didn't have to tell it this thing has an input of lifetime tick A and this thing has an output of lifetime tick A, right? It just sort of like inferred it. So why did it infer it here? Why were we able to, and the terminology here is elide or elision. So why were we able to elide the lifetimes over here, but it really is requiring these lifetimes over here? And my take on this is that these lifetimes here only really have one realistic possibility. There is actually like technically other possibilities that you could have, but there's only one reasonable possibility if the code is written like this, which is this thing, like we have a borrow that's being put in, we have a borrow that's coming out, and so like these borrows should be the lifetime of the borrows should be equivalent here. One lifetime should follow from the next. And so it's happy to elide this. The problem with this is it's not clear what the lifetime of this could be. And you might go, okay, it's obvious to me, it's just the shorter of the two, but what if I wrote you a function that looked like this? What if I said fn empty if second string in first, otherwise like first. It's a great function name. And I have the same signature. And what does this function want to do? Well, if the second string, this y here, exists inside x, right? If x contains a substring of y, then we'll spit out, then we'll give it back the empty string. Otherwise, give back, if it doesn't exist in y, give back x. So let me write it. If x contains y, then we give back an empty string. Otherwise, we give back x itself. What is the ideal lifetimes for this function? Now, we could write tick A, tick A, tick A, throw tick A's on everything, oops, and tick A over here, and the compiler is happy. Build, it's not happy with this one down here. Comment that out. It's not happy with this code down here. Comment that out. And it builds. Right, the code builds. It's happy with this function definition up here. But this is actually kind of bad, because if y is a really short lifetime here, this second string y, if y has a really short lifetime, then the Rust will infer that this outputted lifetime is also very short. But we actually don't need to do that. Watch this. If I take the tick A off y here and just do a ref stir, compiler is still happy. Y, this borrow of y, has no sort of bearing on the lifetime of the outputted string. It really only cares how long x is, because we're either going to return back an empty string, which is perfectly fine to live forever, right? Its lifetime is what we call, there's a special lifetime called tick static, which means it can live as long as it needs to. But in this other case, it may return back x. And so we need to sort of illustrate that this lifetime of the lifetime that we give back might be contingent on the lifetime of x here. But y can live for as little as the duration of the function here, and we're still perfectly fine. Y has no bearing on this output lifetime. So that's why Rust specifically wants you to annotate these lifetimes here. So isn't the example of returning an empty string similarly relevant to our previous function with one parameter where it was eliding? Returning an empty string. Oh, I see. Sorry. So that's what I was saying, where there is some different ways that you could interpret this, which is it is eliding essentially this, which says you have tick A, tick A, tick A. But there could be a scenario where this lifetime here is actually longer than tick A. But the trick, the sort of thing to think about here is, well, if this is the only thing you have as input, then there's really no like lifetime that you could name. If you can't sort of type this lifetime into your code that lives longer, but let's say lives less than forever, you're actually not going to be able to name that lifetime in your code. Like this is sort of like, I can really, the easiest way for me to answer this is like, try and find a counterexample, and you will almost certainly just never find it. Like give me a lifetime that this return value could have that is longer than tick A, or could be longer than tick A, but is not like could live forever, could live for the rest of the program, which we've just learnt as tick static. And so then if you can't do that, which I'm sort of asserting here that you won't be able to do because you just have no lifetimes that you could like name out here, essentially. There's no way to sort of specify that lifetime that you're talking about because Rust needs a value to generate that lifetime from. It's kind of tricky and gnarly to explain with what we've got right now, but if you take my word on that, or you try and disprove me, and if I'm honest, most likely have trouble with that, then it only leaves you with, well, the only other lifetime this output could have, if it's not tied to this, then the only other lifetime it could reasonably have is tick static, this lifetime that could live for the rest of the program. And if that's really what you meant, if you meant that this is a tick static stir, like an empty string, then you could just type tick static here, and you don't even need this tick A over here anyway. So if this was just like return empty string, right? Then this is happier. If it was like return hello, because this is a string literal, it's baked into the program itself, so this string can absolutely live forever, then you could reasonably just type it like this, and it's perfectly fine. And so that's why if you don't specify it, it will just elide this as tick A here and tick A there. And it very, very, occasionally it's not what you wanted, and the elision can sort of bite you a little bit, but it's pretty rare. It's pretty rare. The more likely scenario is that you make a mistake like this, where you tell the compiler that this output lifetime is going to be the shorter of these two, when it doesn't actually need the lifetime isn't dependent on one of the borrows that you've said it is dependent on. And so that's a much more common problem that a more common mistake that people accidentally make. And that's why I won't elide it, in my opinion, is because there are actually quite a few answers here that are perfectly reasonable. It's the lifetime of the output is dependent just on X, just on Y, or is the shorter of both X and Y. Okay, so what do we end up at the very end here? We ended up with some tick A, tick A, tick A, and tick A, like that. So we introduced this named lifetime parameter just after the function's name, and then we specify which borrows are related to that lifetime by throwing the name of that lifetime just after the ampersand and before the type. Note if that one of these was, say, an exclusive reference. So let's say we had Y was an @mute stir like this. The spot that you put the lifetime is not here. It is between, it's like the lifetime is associated to the borrow itself. So you throw it right here. Ref tick A mute stir is the right way to type a lifetime like that. Of course, these aren't mutable. These aren't exclusive references in our case, so we just write it like this. Okay. So this is our sort of like introductory idea to lifetimes and how Rust tracks them. We can also, so that was, oh, sorry. That was our introduction to the idea of lifetimes, especially through, where'd it go? This idea over here, as we saw earlier as well. This is all very relevant to this idea of the tracking of lifetimes and stuff like that. And then we looked at how we annotate those on a function like this, introducing the name, annotating it where it exists. Notice as well, there's one thing that often trips up Rust beginners. Let's say I've let z equals y or something like that, and I want to type z. Often people will go, well, z is a borrow of a string, and since it's borrowed from y, it has a lifetime tick a, and this scenario is okay as far as the Rust compiler is concerned. This will build, but if I say like I have some lifetime tick b, and then I say let's say z is just a string hello, and I say this is now lifetime tick b. It's also happy because this is static. Let a is a string from hello, and then this is a borrow of a, like this, a dot as dir. There we go. Happy now. So you can't just sort of like randomly assert and annotate your own lifetimes in the code yourself, or you can't say like, I'm gonna borrow this, like I'm gonna take a and like borrow it for tick b, or I'm gonna borrow it for tick a. Like this is just not syntax that exists. So whenever you're saying, like, sometimes ampersand appears in a type where you're specifying this is the type that of like my value here. But there's also this ampersand, which is meaning like take a borrow of some value, and you can't just like assert what lifetime that you would like it to have. That's all inferred by the compiler. You can't assert that yourself. So it's one thing to keep in mind that sometimes trips up beginners, but it's something that you'll often just like, at some point you'll run into it, you'll be confused, you'll fight the compiler a little bit, you might ask a question on the forum and you go, oh, okay, I see what was going on here. So don't worry about it too much in advance. Just something you might run into. Okay, so then we had also struct and enum lifetimes over here. So let's say I had a struct that contained a borrow inside it, or let's say an enum where at least one of the variants had a borrow inside it as well. Now you'll notice if you just type this, the compiler is going to be like, no way, not allowed to just do that. And the reason is, imagine we had a function that was like this, which said function foo. I'm actually going to change this to like a string. Yeah, I'll change it to a string. Function foo takes in s, which is a string, a borrow of a string in this case, and then it spits out a struct with borrow. And in fact, we have stirs now as well, so let's be a little cleaner. And actually, no, I need this own thing over here. Fine, we'll leave it as string. And the problem here is if I just said, return back a struct with borrow, where x is this s that's been passed in, this function is happy, but we've sort of like hidden the lifetime from the Rust compiler. So notice that s here really has some lifetime tick a, but we're just giving back a struct, right? We didn't say this struct is like tick a struct with borrow, right? It doesn't know that the input here actually sort of, the lifetime of the input sort of carries into the lifetime of its output, because this struct with borrow should really only be valid as long as this borrow here is valid. This borrow here, which is s here, will only be valid for the lifetime tick a. And so it's almost like we could potentially be able to escape the safety of the Rust compiler if it didn't know how to deal with these lifetimes in a struct. And so essentially, if I ask the compiler, hey, what should I do here? It's actually going to give me the right thing I'm going to guess here. Missing lifetime specifier. You've got x, which is a borrow, inside the struct, but I'm not able to keep track of this borrow. So you might want to consider saying that this struct carries along some lifetime tick a, and this x here, this x is borrowed for that lifetime tick a. So now the interesting thing is that this And it's the same thing applies for the enum here. Throw in a tick A there. This enum may have a lifetime of tick A. This, what the heck? It's happy with that. I didn't know it would elide just like that. Really? Sorry, hang on. This is, oh, now is it oh no, now it's unhappy because this is not pub. This might be another new kind of elision that's joined the language. Let s is struct lifetime foo of let string is string from hello and a borrow of string like that. And s has this struct with borrow. Wow, it's actually eliding this for us, which is very surprising. But what we usually see this as is sort of like this. Oops. So we say that foo has some lifetime tick A that we're keeping track of. This s here includes this lifetime tick A, right? This borrow is valid for some lifetime tick A, and this struct that we're spitting out that contains a borrow is also going to be valid for this lifetime tick A. Right, so this has some lifetime. This struct will only be valid while this s borrow is valid here. So if you have a string that only exists for a very short period of time, then this struct really should only exist for that very short period of time as well. But if you have a string that's going to live for ages, this struct can certainly live for ages. That's maybe a way to sort of help think about it. Now there is sort of, again, this elision that I had not seen before, honestly. Again, the Rust compiler, the Rust language updates every 6 weeks, which sounds like not a lot, but when you use the language for years, it can certainly run away on you. How I, as a Rust programmer of however long ago, would tell the compiler to work out these lifetimes for me is I would get rid of the tick A here, I'd get rid of the tick A here, and where we have this struct of tick A, I can actually use this special lifetime called tick underscore, which essentially means you figure out this lifetime here, it should be pretty obvious. That's essentially what it means. Figure out the lifetime, it should be obvious. And since we have s is a borrow here, it'll go, right, that's going to be some lifetime tick A, and this should obviously be tick A as well. We have a borrow in, a borrow out, it's the same thing as when we saw as what we saw here. Borrow in, borrow comes out, borrow comes in, borrow comes out. But apparently you can now leave off this whole tick underscore thing as well, and it will also elide that, which, yeah, that's news to me as well. But I generally prefer, it feels a little strange to me. I'm sure I would get used to it, but I like to sort of see that the struct does borrow from something inside as opposed to just looking like it'll live for, I'll be the owner and there's no borrows associated with it, essentially. So let's just put in the long form for now, but knowing that there is a couple different ways you can get the compiler to infer those lifetimes for you. Question: why couldn't we have done this for our previous example with the empty string elision? Why couldn't we have used tick underscore for the counter example you talked about earlier? So this one was it this function here that we were talking about, or was it this function here? As something like this function here. Which signature were we looking at? And also, by the way, you absolutely can do that here as well, where it will infer it. It'll go, yep, I know what the lifetime of that thing should be, and it's fine with that. First word. Oh yeah, okay, first word. Yes, you can do that. You can do this kind of elision as well. You go, this should be obvious, and it goes, great, it is obvious. This is a borrow in, this is a borrow out, so the lifetime of this will be equal to the lifetime of this. And so it will infer this lifetime for us as well. That's exactly what's happening when we just write the code like this. So again, most of the time, don't worry about writing in the exact lifetimes until the compiler goes, I can't figure it out. Right? While the compiler can figure it out, you don't need that extra noise. It's generally pretty obvious as a human reading the code what's going on. So let the compiler do the work for you. When the compiler complains, and in fact, I've broken my own rules exactly right here. When the compiler complains, then you go through and which lifetime is which and that kind of stuff. And then very rarely will you get a problem where the lifetime that the compiler infers is worse than the lifetime that you actually want, if that makes sense. And that also, I guess, just brings us very quickly, since we've been talking about this for a while now, to this elision here, which is, in fact, the first word example that I was talking about before, where instead of specifying all the lifetimes manually, which I believe I was planning to do, but we ended up getting there earlier anyway, right? Instead of specifying them all, say, manually like this, the compiler will often let you elide the lifetimes like that or like this, and you know, all is happy. And this is just also, this is a slightly more functional way of doing this first word thing as well. Split once on the first space character, and then it'll split it into before and after potentially, right? It's an option. Just map that into the before part, and if it's there, spit it out. If it's not, then give back the whole string. And again, the lifetimes, there are a lot of lifetimes that are getting tracked around here, but the compiler is very good at that. And so, like, I don't have to worry about all the lifetimes here. It's figured it out and gone, yep, this all follows the rules that we expect. What if you declare the lifetime in a function signature, but you break it when you call the function? I'm guessing the borrow check will pick it up. All right, that's a great question. So if we have some function foo, in fact, you know what? No, let's not do some function foo. Let's grab this function here that we've written, function longest. We'll do it in main as well. So function longest we've now got here. This tick bead really doesn't need to exist anymore. And so let's say we have this string here, which is a string with a very long lifetime. And then we have a string with a shorter lifetime, like that. And then we say let longer equals the longest between string and short, like that. If we use it down here, longer, then it's going to be perfectly happy. All right, and it spits out, I guess, if they're equal, it chooses the second one. Let's just make the shorter one longer, so it's very obvious. And there you go. Because the lifetime it infers is this is a long lifetime from here all the way to here. This is a short lifetime from here to here. And longer is only existing within this short lifetime, so everything's perfectly happy. The borrow checker doesn't care. But we can try and like skirt our way around the borrow checker by doing something like this. So let's say let longer. Then we say down here, longer is equal to this. This is still happy because although longer looks like its lifetime is all the way to here, but from this function here, it should infer that the lifetime is this. It sees that since longer isn't used in this section here, it can shorten the lifetime in order to make the program compile. So to be clear, this idea of shortening the lifetimes automatically, it's something called non-lexical lifetimes, NLL, that appeared in Rust in 2018. And it only does this shortening if it finds that it needs to. If it finds that your program won't build, it'll try and shorten your lifetimes, is one way to think about it. And if it shortening the lifetime solves the problem, makes the program compile, then it's like, great, we've fixed that. But if I then move this print line down here, you'll see that suddenly things aren't so happy. Because the lifetime, the shortest the lifetime can realistically be is at the end of this print line here. But this short here only exists over this period. So what kind of error message do we get? We get this. Short does not live long enough. The borrow checker has stopped us in our tracks. So it says that short here is borrowed and it doesn't live long enough. The borrow, its short is dropped at the end of this scope here on line 28, right? It's dropped here while it's still borrowed by longer down here, right? It's later used on line 30. And so the borrow checker stops us from letting this code run. And to be clear, in other languages, this would be something like a stack use after free. So in C or C++ or something like that, you get a memory safety vulnerability. Hackers are in your computer and they are leaking, all your data and ransoming your computers and all that. Very, very scary, horrible stuff. So the borrow checker tracks all these lifetimes for us. It's very nice. Very nice of it. Okay, global in Rust. So are you asking about global data? I might need a little more than that to work with, if that's all right. Cool. So that's all that. No more dangling references. Hooray! So that's our sort of like vague idea of lifetimes. Lifetimes go, you know, I think we've had a pretty decent, where am I? Up here. I think we've had a pretty decent introduction to the premise of lifetimes and sort of the fundamental ideas behind lifetimes. Lifetimes take most Rust programmers a few months to really sort of like understand quite deeply. Sometimes it can, if you use Rust less, it can take, you know, it could take a year or maybe even longer to really set in. But often you don't need like a really deep understanding to use the language. You sort of need like that medium understanding that we're hoping to get to within maybe the next week or so, where you may not be able to answer every single thing about it, but you should hopefully be able to like follow the error messages when the compiler tells you something's wrong and use that to try and get a program that builds and or potentially be able to spot a situation where the compiler says, hey, I'm not building this, and you go, oh right, that's because my whole approach here is just like completely unsound, and it's just going to cause it will cause like memory vulnerabilities if the compiler were to let this through, and I need a completely different approach potentially. What if we make it global? Does that mean the lifetime would extend indefinitely? Right, so that's your question there. If I said let x is an static x is an i32 let's say is a string from hello, like that. Yes, x here has the lifetime tick static, right? So again, I can't really sort of type this here. The compiler won't let me, but this, if I were to like borrow from x, static y is a borrow of x, like this. Well, actually, maybe it'll let me type it like this. Then yeah, okay, it's happy with this. If I borrow from x, then I will get a tick static string. So the borrow will be the borrow is valid for the entire lifetime of the program, which is quite nice. Okay. And this is how you do globals in Rust. Generally, we avoid globals in Rust, and Rust makes it hard to deal with globals because globals can be quite dangerous, and Rust makes you avoid danger at all costs. Cool. Okay, great. All right, so the last little bit here that we'll end off with is smart pointers. So we'll look at 3 as part of our quick little look in here, and I don't have any sort of practical exercise to go through, but we'll just chat through them a little bit. So we've already seen, just again, T, we talk about this all the time, just sort of any standard type T, whether let's say, strings may be a bad example, if it's like an i32, let's say, or something like that, the location of this type, or if it's some struct that you made, for example, the location of this is on the stack. Even if you have like a vec or something like that, a vec, which I keep saying is like vec stores things on the heap, which is like malloc memory and all that. Vec realist actually is a struct. Vec is, a struct vec that actually lives on the stack itself. The things that live on the stack is a pointer, pointer, len, and the capacity. So it's basically 3 pointer-sized values essentially, and the pointer points to the the actual vector itself. This is the stuff that's on the heap, right? This here exists on the heap. It was malloced, but the pointer, len, and capacity itself that really make up the vec still do exist on the stack. It's just that the stack values have a pointer over here that send you to the heap. So by default, things live on the stack. And the borrowing here is, the borrowing semantics is that it's not, a T is not borrowed, right? You own this T, you are the owner. But a limitation that we have to work with is that any sort of T that you just declare, the T must have a known size, right? This was the idea of like, we can't write we can't have like a slice. Like we can't have a slice that isn't behind a reference or isn't behind like some sort of other indirection, because we don't know what the size of a stir is. So in our case, let's say we had x's is a slice of I32s, and it's going to be equal to like 1, 2, 3, 4, 5, right? I can't then say like let y's, which is a slice of I32s, equals dereference x's, because it's going to say it doesn't know the size for values of type slice I32 cannot be known at compile time. In other words, it's not sized. So this is like a serious problem for things, for just variables that you're declaring, is that if they don't have a known size at compile time, then you simply can't declare them just simply like this. So instead, you have to put some indirection behind it. The indirections that we've learned so far are a shared borrow and exclusive borrows as well. So I could say x's is a shared borrow here, or I could also say, for example, use an exclusive borrow, which also provides that same kind of indirection here, and that's also fine. But there are other pointers that we can use, right? The sort of trouble here is that what if I just want that indirection? I just want the fact that instead of the value itself I'm storing a pointer that I know the size of, but I don't want this whole idea of lifetimes to come along with it, or I want some other things instead. I just don't want this shared borrow and exclusive borrow and I don't want to deal with the lifetimes. I just want that indirection so I know the size of my thing, but maybe I'm still the owner, or I want some other thing. These are the different smart pointers that we have available to us. So the most simple of which is box of t, right? So in our case, that would look like this, a box of an I32 slice, like that. And the way we create a box out of something like this is just simply with box new, like this. It's not going to be happy with this because, we'd have to say box, box into box slice, right? Box into box slice of, converts it, yeah. These things are gnarly at best to deal with, because the question, okay, I don't want to go too deep into it essentially, and if you're interested, of course, ask on the forum, but I'm wary of time. I don't want to go 20 minutes over time explaining things that aren't really that relevant to the course, but we can also have types here, like a slice of I32, which is behind a box. A box is really just a pointer. This unique of t is eventually, we'll get down there, is just a pointer to some type t, and that pointer points to the heap. Box of t still implies if you own the box of t, you own the t inside, so that's perfectly fine. The limitation of a box, like why don't we just box everything then? Because a t is, must have this known size, and but a box t is still the same stuff. You still own the t and can still use it for everything. But it can even support values where you don't quite know the size. Why don't we use it everywhere? The answer is for performance reasons. Allocating memory and freeing and all that takes time. It can often add up over time. And if you care about performance, boxing everything can be a serious issue. And languages like Java, languages like Python, languages like Ruby, I don't know, there's plenty of examples here. Languages like JavaScript, whatever, are very keen to box tons of stuff. Every object in Java is boxed. Every value in Python is boxed. Every object in JavaScript is boxed. And so that's why a lot of the time if you sort of need to drop down that level for more performance, Rust can sort of give you that option if that's what you're sort of looking for. So box t is really honestly not that special. There's not too much going on with it. It just is like, it's a t, but instead of that t living on the stack, the t lives on the heap, right? That t is malloced. And then you just sort of store the pointer to it, just like you would in say C. You just store a pointer to that t value, but it gives you a bunch of functions to use. It makes it very convenient. But yeah, it's rather simple. And it also frees when it goes out of scope. So when you drop a box, when a box goes out of scope, it runs a little bit of code, which just says free the pointer, which is also quite nice. We also have RC, reference counted of T. Similarly to a box, this lives on the heap. The thing that's convenient about a reference counted T is it acts like you're sharing the T. It acts like you're sharing the type. So let's say I had some string where my string was like, yeah, let's do it this way. Let my string is a string that says hello world. And I want to share this string, like the string object itself, around a whole bunch of places, right? And so that would be, you know, if I have some function foo, the way we know how to do that is that it would take in a borrow of the string. I know we've just learned about stirs, but let's say I really wanted to actually pass around this string object. And so we say, okay, yeah, we use borrows there, and that's fine. But the problem is, what if I want to pass it to this function foo, or a whole bunch of other different things, and some of them might need it longer than I'm able to store it over here? Let's say that's our sort of scenario that we're in. In that scenario, we'd get a lifetime error. The borrow checker would come, you know, banging at our door, and we'd go, you're trying to like pass off borrows of this to all these other places, but they might need it longer than you're able to keep it alive for. And so the idea of a reference counted value is that I can say let reference counted equals RC from my string, let's say, and it's RC new rather. RC new my string. So this has type RC of string. And over here, we'll take RC of string. Let's say we have some function foo. Let's say we have some function bar and some function baz that all want to take this string in. And let's say this string only exists for a very short lifetime as well. In here. Then the really cool thing is let longer, and then longer down here is going to be equal to reference counted. Reference counted strings implement the clone function a little differently. So instead of actually cloning the string, making a whole new string with the same stuff and then giving you that back, instead they just take this reference counted thing, which contains the string inside it, and increment a number. The number starts at 1 when I create it, and every time I clone it, it increases that number by 1. So we go, here we have 1, and then when we do clone here, it increments it to 2. And then every time this RC is dropped, and they're all pointing to the same string as well, which is quite interesting. Every time this RC is dropped, it decrements the counter by 1. Right, so this longer is reference counter.clone, and let's say down here we go foo of longer and pass that out. This original RC here is going to go out of scope right here, and this looks like the borrow checker should be really pissed off about this, right? This is going to go out of scope right here, but I use it over here later. And the reason this works is that, again, starts off with a counter of 1. When we clone it, it increments the counter to 2. Then this one here is dropped right at the end of this scope, and it decrements the counter to 1, which is not 0, so it doesn't free the memory. Then we pass this RC into foo, it gets transferred into here and then dropped at the end of foo. And when foo drops it, the counter drops from 1 to 0. It goes, great, the counter's 0, no one else is using this anymore. And so it then frees the memory after all of that. And so I can actually go like foo of, let me make longer 1, longer 2, longer 3, longer 1, longer 2, longer 3, and then foo of longer 1, bar and baz of longer 2 and longer 3. I can just make all kinds of these copies around the place, and it never actually creates a second string at any point. All these clones are actually very fast because they're just incrementing a number, and then every time each function is done with it, it'll drop 1 off the number until eventually the count goes to 0 and it actually frees this underlying string at the very end. Now the caveat here is great. You know, everyone has these own values and the string will live as long as you need it to. It will only ever possibly like disappear once you drop yours potentially. Is that you can only have shared access to the string itself. If you could say mutate the string, if you could get exclusive access to this inner string, or if you could say get ownership of this inner string, then that would be no good, because these two really are talking about this same string. And so we can't have these two functions both be trying to mutate it at the same time. So that is like explicitly unsound, not okay in Rust. And so a limitation of RC is that you only get shared access to the inner value. So in this case, we could only read from this string. So that's a limitation. So it's the borrowing is you can now share a value without any lifetime. It'll live as long as you possibly need it to, but it has some limitations. You can only read from it because it's a shared borrow. Borrow is not really the right word here, but shared access only. Reference counting does have a bit of a performance overhead. You still do need to increment that counter, and you do need to decrement the counter each time. If you have tons of things that are reference counted, then it can kind of add up, but it's pretty rare, to be honest. Reference counting is usually pretty fast. However, one rather serious problem with reference counting is cycles. So I think I saw someone say, Miguel says, basically like manual Java. So Java has a garbage collector, and the one thing that sort of substantially differentiates well, there's quite a few things, but one really important idea that differentiates garbage collectors and reference counting is that imagine I had a reference count of struct1, let's say. I had a reference count. So let's say I had some struct1, struct1. And inside struct1, we had a RC is going to be I have to write this as option. If you're writing the code yourself, you'll have to use option and you'll end up figuring out why. But just for simplicity, I'm going to write RC of struct2, right, is inside a struct1. And if I have a struct of struct2, and struct2 inside it has a field called RC, which is an RC of struct1, let's say. Right, and again, these are both going to need to be options if you're doing this yourself, and you'll figure out why, but not super important for us. The problem, and that looks like a 2, I'm now realizing, but it really is a 1, like that. If I then create these two values, like I have an RC of struct1, and struct1 points to struct2, struct2 points to struct1, and then I drop this one here, well, the RC of struct1 that is sort of shared between this and this here have count 2, and this RC of struct2, which is not shared anywhere else, has a count of 1. I drop the one that I sort of like have access to, right? This is sort of my window into this whole world down here. But the count doesn't drop to 0 and free all the memory, it drops to 1, because we still have this one over here and this one over here pointing at each other, right? And these both end up getting stuck with a count of 1. And so even though no one is pointing into either of these really are like candidate to be freed. We don't need it anymore. Reference counted cycles, see we have a cycle here goes to here and then this goes back, will never end up freeing themselves. This will end up creating a memory leak, sadly. Whereas a garbage collector, which is much slower but potentially more accurate, is able to come through and say, well, no one else is pointing into any of these, so I'm going to go ahead and free all this for you. That's sort of like a limitation of reference counting as opposed to garbage collection. But garbage collection is far slower and brings a whole bunch of baggage along with it, which I'm sure we'll find some time to talk about sometime. So yes, so hang on, aren't objects essentially always unique pointers in Rust? No. Unique pointer, if you're coming from C++, is box in Rust. So you generally write when your thing is a heap allocation with box. So all we've been talking about, or the majority of what we've been talking about, have been stack values in Rust. So no, not everything is a unique pointer in Rust. And yes, if you're coming from C++, box is unique pointer, RC is shared pointer. And RC is a little, actually, shared pointer is actually something called, if you have coming from C++, shared pointer is actually something called arc, which we'll talk about in week 9. And this is something where Rust has certainly a distinct advantage over C++ in this specific case here. But that's sort of just a little teaser. We'll talk about it more in week 9. And then finally, this is the last one I very quickly want to talk about, is RefCell. RefCell is a really interesting type where essentially what it allows you to do is almost like defer the borrow checking rules to runtime. So instead of the borrow checker checking all the stuff as you know as the compiler does, checking checking your ownership rules and whether you can have 2 exclusive borrows at the same time and all that, instead of it doing it at compile time, it defers that work until runtime. And if you sort of put yourself in a situation where the rules would be violated, it will panic your code instead. It'll crash your code. So RefCell is a little bit of like an anti-pattern. You want to try and avoid it if you can, because you'd rather be hit by those errors at compile time, so your program that you build is more likely to be correct. But sometimes you do really need it, or it can be really handy to write some code quickly. And again, it just sort of, if you go, yeah, I know this is going to be okay, and but the borrow checker won't get off your back. It's complaining about your program that you're very certain is correct, but the borrow checker is not convinced of. You could defer that borrow checking until runtime, and it lets you take it lets you essentially. The trick with RefCell is probably easiest to sort of view in terms of the documentation. RefCell. The idea that the thing that's really cool about RefCell is if I say want to, RefCell is sort of generic, it takes some type T. So you put a RefCell around some type T like an i32 or a string or whatever you want. And you say, I want to borrow that. I want to get like a shared borrow on it. Then you can do that with a shared borrow on the RefCell itself. And you can also say, I want to borrow exclusively, give me an exclusive borrow on the value. And you can also do that with just a shared borrow on self. And so that looks very scary. A shared borrow on self lets you get an exclusive borrow on the inside T, which again is scary because if I have one RefCell, I can say, give me exclusive borrow, exclusive borrow, exclusive borrow on many shared borrows of the RefCell, and just get all these exclusive borrows to the inner value at the same time. Very scary. But the trick is, if you have an exclusive borrow that you're currently using, then this function call will end up panicking at runtime because it checks it for you, and it'll crash your code. And so there's no possibility of unsoundness and breaking Rust's rules. Note, it's also worth noting that this is not like magic. The way RefCell is implemented is not compiler magic. It's not like Rust, the language, sort of built in this idea of a RefCell. It's actually just like code that someone wrote. And like you could implement RefCell yourself. Maybe at the very end of this course, it's a nice exercise to try and do yourself. It's certainly like very tricky, and you need something called unsafe code to make that work. But anyone could make RefCell themselves. It's not a special type to get around the borrow checking rules. It's all sort of above board, which is, I think, rather cool as well. So at the end of the day, the message I want to take you to go away with is that there's some smart pointers here to like play around with and to think about. In this case, box, RC, and RefCell might be of particular interest to you. There are some more as well. But like, for example, there's other cell types other than RefCell. RefCell is often the most, what's the word? Sort of like flexible of them all. But you also have cell here. You have unsafe cell that again is you have to be very knowledgeable about Rust to confidently use this one. So the main two is cell and RefCell. Have a look at cell in your own time as well. Cell is quite an interesting one, and try and convince yourself why cell is like sound to exist, why it doesn't break Rust's rules. But otherwise, yeah, those are most of the most of the smart pointer types that are particularly relevant to this course. Okay, let's cap it off there. I think that's a nice spot to sort of leave things off. String is also stored in the stack. So string is stored on the stack. Again, the distinction here is it's just like a vec essentially, where if you have, let my string equals string from hello, right? Hello. The trick here is that my string essentially looks like a struct string, which looks like it has a pointer, it has a length, and it has a capacity. And so these three things get stored on the stack in my string here. These three, in a 64-bit computer, these will each be 8 bytes. So these 24 bytes, and it's always 24 on a 64-bit computer, will be stored on the stack. But this pointer will point off, like, let's say this here is the stack and this side here is the heap. This pointer will point off to, the bytes, HELLO, that live on the heap over here. And this might be of any length. In fact, the length will be this length that we've stored on the stack here, but this could be dynamic. This could be no elements. This could have, 5 characters, or it could have 1,000,000 characters as well. So that's sort of the distinction there. Does string live on the stack or the heap? Kind of like both in a certain sense. Cool. So any other questions? So we're wrapping up the lecture. Thank you everyone for coming. Thank you everyone for dealing with the internet dropouts and, bearing with me as I try and make this setup work and keep getting these lectures out. As a reminder, next week's content should be more chill, right? This is week 3. Is it week 3 or week 4? What week are we in? I should know this, I think. Let me double check. It's week 3 that we're in. And week 4's content is documentation, testing, modularity. I think that's a lot more chill than anything that we've covered yet. Week 5 is definitely going to be, week 5 is going to be a fun week in that it's going to be complicated again and have some pretty gnarly stuff to play around with. Next week is going to be a little more chill. I hate to say this. It doesn't feel super nice for me to say, but it's something that people should probably be aware of regardless. Census date is at the end of week 4, I believe, week 4 Sunday. So next week Sunday. As it really genuinely does pain me to say this, and I don't want to say it, but I'm going to say it anyway because there is, some students who this is, that you'll want to spend some time thinking about this. The end of week 4 is sort of where you might want to take a quick pause and go, how am I feeling in this course? How am I feeling about the speed of this? And how am I sort of getting along with Rust and doing okay? And so I think most people who have made it to, past the prereqs into this course probably are aware of how census works and how it relates to academic and financial liability and all that. So it's just that point where you want to have a quick moment to stop and think, am I enjoying the course? If you're finding the course difficult, that's almost certainly to be expected. I think lots of students came up to me before this course ever ran and said, hey, is this going to be an easy course or is this going to be a hard course? And I'd always go that's probably not the right question to ask, to be honest. But I'm always going to lean on the side of going, this is probably going to be a hard course and it's probably going to be a relatively high workload course. So if you're enjoying yourself and you are sort of eventually coming to understand these concepts, even if it's a week or 2 behind or whatever it is, then that's perfectly normal and okay. And if you're otherwise having fun and want to keep going with the course, then we really would love to have you all. If you're not enjoying the course, and or you're just not getting the ideas and you're really having a particularly bad time, that's when you might want to consider maybe the course isn't for me, at least for now. And it's very sad, and I would very much love for the number of students in that bucket to be 0, but there's going to be, you know, at least 1 or 2 at an absolute minimum for sure. And so it's just something to be aware of. Again, it's making me sad just like talking about this. So I'm going to stop talking about this so I can be happy again. But just keep that in mind for sure. And if you're in that position right now, if you can like sort of foresee that you are in that position right now and you like don't want to give up, talk to us, right? Course forum or the course email, or sort of you can talk to a tutor in a workshop and that kind of stuff. Let us know the position you're in and think of what we can do to help you. If it's that you're not enjoying the course, you're not enjoying certain aspects, let us know. Also, there's the feedback form available as well. Let us know so we can try and fix it for you and try and keep you in the course and get you through to the end. And if you're struggling with things in particular, also let us know, and maybe we can set up some certain things for like revision or extra content and that kind of thing to help you with that. So I want to keep everyone that I possibly can in this course and enjoying it. But if you're really not enjoying things and you don't think there's going to be a way for you to enjoy things, then I don't want to hold anyone against their will. So that's where I'll leave that. Daniel says, need to watch this again. Zoned out a couple of times here. Oh, speaking of watching again. And in fact, I'm going to learn my lesson here and go to a private browser. Let me make a quick recommendation. Like, this is just my personal recommendation. Jon Gjengset is an absolutely fantastic Rust educator, Rust content creator. And he also has sort of live videos that are certainly better than what I'm able to produce, to be honest, that talk about these similar ideas, whether it's talking about lifetimes or smart pointers and this idea of interior mutability with things like RefCell or iterators, or there's all kinds of videos that he's got on his channel. And even just some where he's like building a big program in Rust, implementing and optimizing a Wordle solver in Rust, which is a 6-hour video. Absolutely excellent content creator. I love everything that he creates. And in particular, something like lifetime annotations. I believe this is the video he does with StirSplit. And I'll just double check. Yes, StirSplit here. His content is often a little more leaning towards intermediate in its assumptions about Rust, which is sort of like, there's a tricky thing for us to deal with in the course, is that a lot of the time it's a lot easier to talk about the ideas of Rust and to really teach you deeply about the ideas of Rust once you already know how to write Rust. And that's sort of where I was talking about in that level where it's like you can use Rust and follow the compiler complaining at you to get to where you need to get to, but you don't have that super deep fundamental understanding about a lot of these ideas. Jon's channel here is really great at getting you from that I know how to like use it, or I know I can read Rust, and I can read and write Rust, writing maybe to a certain extent. If it gets really complicated, then maybe I can struggle or not get there in the end. Taking you from there to that really fundamental understanding, his channel is absolutely excellent at. Whereas in the course, we need to keep the students who are sort of far further down in like the I'm still getting to grips with even just like the syntax. We have to keep them in mind, so we have a slightly different target audience. But anyway, that's an excellent channel to keep in mind. Another one that's also really good that I can personally recommend is fasterthanlime, which is a slightly smaller channel here. And I think he talks about ideas that are outside Rust as well. He also makes some absolutely killer blog posts, which hopefully maybe here. Yes, fasterthanli.me. And there's some really great blog posts that I think we've already recommended one or two in the course webpage here and there. But some articles, rather, not blog posts, articles that are seriously very interesting, and they're usually like I find that a lot of these are it says like it's an 80-minute read, and it's more like I think the thing here is it's more like 30 minutes to read the text, but maybe more like 80 minutes to understand it. So don't get scared off too much by like the estimated time to read it. But they genuinely can be very interesting. So yeah, I guess that is pretty long, isn't it? Oh, my teeth are getting green screened. That's funny. Okay. So any questions before we oh, and Miguel likes no boilerplate as well. I think I've seen a couple of them, but not enough to give a personal recommendation. But I've certainly I think I've seen one or two of their videos. But Miguel seems to recommend them on the contingency that sometimes they're a bit information dense. Okay. Yes, it is. This is a rather long article. There's some shorter ones as well. So any last questions before I flick the lecture off? Thank you all for coming once again. I hope we learned some new stuff. I'll give, if I don't hear any questions by 45 seconds past, then we'll cut things off. Not for the faint-hearted. But they're really good. 25-minute read. A Rust match made in hell. I mean, honestly, like, the text goes faster than you'd think, I feel like. The text goes faster than you think. Because it's very, like, long vertically, but a lot of it is just sort of like him talking to himself. So it'll be like, here's some code, and then like, oh, a little thing here, the code changes slightly, a little thing here, the code changes slightly, a little thing here, the code changes slightly. And so like, although that is like, 3 A4 pages of text, it maybe only takes like 1 or 2 minutes to read. Yeah. Okay, I'm not seeing any questions. 2 weeks to read the Rust book, yeah. I'm not seeing any other questions, so I'm going to leave it there. We'll see you all in the workshops. This week. Oh, that just reminded me. Monday is a public holiday, I think. I think week 4 Monday is a public holiday, which kind of sucks. So we might have to reschedule the lecture. I might record something. I don't know what I'm going to do yet. I'll make an announcement. I got to figure out what I want to do. But I think it's a public holiday, so I'll double check that. You look out for an announcement as usual. Yeah, I'll figure that out and let you know what we're gonna do. But I think the next lecture, next week's Monday lecture is a public holiday. So regardless, assuming I'm not wrong here, enjoy your public holiday off as well. And we'll see you in the workshops this week. Very excited to do that. And we'll address feedback in next week's first lecture again, as mentioned earlier on. All right, thank you everyone. Thank you for coming. See you in the workshops, and have a good night. Yes. See you later.